Hello everybody, welcome to the second day of ICAPS 2016 in the middle of London. I'm very pleased that so many could get up so early to listen to Susanne Biundo. Biundo is probably has the biggest planning group in entire Germany. She is in the field for 3 decades already. And she got her PhD from Causal University in '89, and then switched to Legality, that's a German research center for artificial intelligence, and was a senior researcher in there for 10 years. And then she swapped to a professorship in Ulm, where she still is, and where she works now for 20 years, I think. And she's probably not known to everybody for being one of the founders of the Planet. This was a European group of researchers in 1998 or so, for 5 years. That's almost the time when I got together with her. She was organizing ECP in the castle in Durham in '99. And since then we met here and there. One PhD of her is a friend of mine. We meet in regularly special interest group of planning in Germany. And she now has a big group, and also she is heading what is called a collaborative research center in Germany. It's a big thing. It's called Companion Technologies. We will probably listen to some of these issues in the talk. And I'm very proud to have her here. I'm also proud that she has one of my lost papers on her webpage she does not know, which was deterministic planning with BDDs. That was a poster paper in ECP which dropped out, but she has it on a webpage, so you might check. But here we will listen to making plans for human users. So the connection of getting planners into the world and close to us. And I'm very excited to have her here and listen to this talk. Susanne, it's your stage.
Okay. Yeah, thank you very much, Stefan, for your kind introduction, and thank you very much for inviting me to give a talk at ICAPS, also a great honor. Yes, and I'm pleased to talk about making plans for human users. And when we look at applications, so a big area where applications, and in particular where it is relevant for planners to make plans for human users, is actually these areas where plans are executed by human users. Namely, for example, in mission planning, where you have, in case of earthquakes or floodings or things like that, you have to have disaster relief missions, which are very complex logistic tasks, and there you have to put in place all the stuff, the material, the relief teams and so on, and this is quite complex, and the plans for that are made beforehand and then are adapted in case, and also are adapted during execution. Another application area is, of course, project planning. So if you think of big projects, big construction projects like constructing airports or moving airports, or constructing new tram lines in big cities and so on, this is also an area where planning could help very much. Intelligent planning technology can help very much, but always users are involved, not only in the execution of the plans, but probably also in their generation. And the third application area is personal assistance, not only concerning the personal agenda, but particularly helping people in complex tasks for which they are not very experienced, for example. So, and we can observe 2 basic missions of user-centered planning. The one is to create plans as recommendations for actions. And this appears, for example, in if you have digital user manuals or operating instructions, So here in this picture we see a worker who is working in a training shop, and he is trained to install the cabling of a vehicle, and you can see that he has a head-mounted display, and the instructions are given over this head-mounted display to the user. So in this case, the task of a planning system would be to create a plan of action, to derive concrete instructions for the user, and ideally these would be individually adapted to the user, adapted to his background knowledge and so on, and then present them in an adequate way to the user. The second area where that are relevant for user-centered planning is the case where you create plans in collaboration with the human user. This, for example, is in project planning. This is also in personal assistance, where the user is really happy to have a system that assists, but he probably wouldn't like to give control completely to the system. So he would like to have at least a part of the control at himself, and therefore it is essential that the user gets involved into the process, so that the system helps, for example, in generating uncritical parts of the problem, in working on uncritical parts of the problem, but leaving the critical ones to the user, at least insofar as the user may be asked about his opinion about the system's recommendations, for example. And this means we have to realize really a mixed, what we call a mixed initiative kind of planning. So that means the challenges we are faced with are that, first of all, the plans, and in many cases also the planning processes, have to be understandable to humans. The plans and the decisions of the system should be explained, and both these points are relevant in view of transparency of the system. So the user might have only trust in the system if the system is able to explain its recommendations and also explain how it achieved these recommendations and what are the reasons for recommending. Plans have to be cooperatively developed, and then plan execution has to be monitored so that the assistance system is always able to recognize whether the user follows or the plan or whether the user deviates from it, and it has to recognize whether these deviations are critical or not in view of the overall goal that has to be achieved. And if a plan is not properly executed, if execution failures occur, the user makes the wrong decision or something like that, then the system should be able to repair this plan and, if possible, and to come up with a modified or new solution to the problem. And plans and the explanation of plans have to be presented in an adequate manner to the user. So before introducing how we use intelligent planning technology for user-centered planning, let us have a look at how humans do plan. So, for example, if we have the task to give a talk at ICAPS in London, then yes, we first of all are happy to do so because the paper is accepted or we are even invited to give a talk. And in principle, we know what to do. Yeah? We know what to do. We have two main tasks, namely, we have to prepare the talk in some way, and we have to travel to London and give the talk there. So that is very well known, and we know some few other things. So we know giving the talk, we have to select the topic, we have to prepare the talk, and then it is essential that the talk and the slides are really ready at the time we have to give the presentation. So this is essential. Concerning the travel plan, we know we have to plan for the stay, we have to plan for the travel, and afterwards we have to execute the travel plan. And concerning the travel itself, we always have various options. We could just contact our travel agency, we can plan for driving by car, for flying, or for doing a train ride, and we can choose among these options. And here we see that planning is done, or several things are essential. One is that we do start from a very abstract task, and we refine it stepwise. Another thing we can observe is that some actions or some tasks have to be executed in an order, have to be ordered. Other points it is not so essential to have an order. So, for example, to collect the material and produce the slides is something that could be done concurrently or interleaved or whatever. And we have causal relationships. So here we need to know the talk has to be ready before it can be actually presented, and we have various options. And now the question is, how does this relate to automated planning? So we have a stepwise refinement of complex tasks. We have nonlinear planning. We have concurrency. We have causal reasoning, and we use how to perform certain tasks. And that means we can rely on known plans, known subplans, and have not always do planning from scratch, and also we do not have to plan in the order in which the actions finally have to be executed. So, and the answer to this question is, well, yes, because we have two important planning paradigms available. One is called partial order causal link planning, and was introduced first by McAllister and Rosenblit in 1991. Which is a planning formalism which basically relies on the explicit reasoning about causal relationships between actions, and also about this nonlinearity. And on the other hand, we have the hierarchical task networks as introduced by Errol, Händler, and Now in 1994. And here we have this principle of decomposing abstract tasks over a cascade of levels, until we reach a level where all actions or all tasks are primitive and can be executed. And in 2001 at the ECP, European Conference on Planning, we came up with a suggestion for a framework we called hybrid planning. And this hybrid planning approach is a fusion of these both paradigms, partial order causal link planning and hierarchical task network planning. And this conference, by the way, ECP 2001, was held in Toledo in Spain. And at this event actually was giving birth to ICAPS, because at this event we decided to join the American and the European planning conferences into this ICAPS, where we have the 26th edition right now. Well, what about hybrid planning? So this formalism extends over a pure fusion of partial order causal link planning and HTN planning by a well-founded integration of action and state abstraction. We do not only have abstract tasks, we also have abstract state descriptions. We have declarative descriptions, we have even pre- and post-conditions at abstract tasks, and we have methods, like in HTN planning, that specify predefined solution for various, for the abstract tasks, namely by providing plans for these. And we have the new notion of decomposition axioms that are in some sense the pendant to these methods, because they are used to relate abstract and primitive state features. So concerning the formal background, we rely on a language that is basically many-sorted first-order logic. So that means we have a typed system and a typed logic, and we have a hierarchy of concepts. So like in this example for a logistics domain, we have as a most abstract notion a transportation means, and we can and these transportation means can be vessels, aircraft, or vehicles, and we can refine this even more and say, well, a vehicle is a jeep or a truck or bus or something. This is for the syntax, and concerning the semantics, we have a logic-based state transition semantics, which means that states are viewed as interpretations of formulae, and the elementary operations represent single-state transitions. And these elementary operations are add and delete operations, which on the semantic level just add or delete tuples from predicates, from relations. Well, to give an example, we have abstract tasks, like here this transportation task is defined as usual, so we have a cargo. So here we have the types in conjunction with the variable symbols. So that means that helps us to find proper instantiations of these tasks always, and restrict the search space in the sense that we do not instantiate something useless. So we have this transportation, we have a cargo and a transportation means and two locations. L1 is the current location, and L2 is the destination. And this is defined as usual, so we have preconditions of these abstract tasks, namely that the cargo has to be at location 1, and the transportation means has to be available to do the transport from location 1 to location 2. And the postconditions are that neither the cargo nor the transportation means are anymore at location 1, and both are at location 2. And a concrete or primitive task in this context is one for driving. So here we have also the cargo and the locations, but here we have a vehicle. And the precondition of this action is actually that both are at the location 1. The cargo is in the vehicle, and there exists a road connection between these two locations. So, and please note that this vehicle is also something that could be refined according to the type hierarchy. So we can have a truck or a jeep, or that may depend on the cargo. Well, these available predicate in these abstract tasks used as a precondition is an abstract state feature. And the decomposition axioms are used, so they relate abstract and concrete state features. And the decomposition axioms are used to refine these abstract state features according to these equivalents. So that means the axiom is always such an equivalence, in some sense defining these available predicate in this case. And this means transportation means is available if it, for example, if for example there exists a vehicle and this transportation means is just this vehicle. It is the location, located at the location 1, and there exists a road connection between the two locations. Or there exists a plane and two airports, for which the following holds. The transportation means is this plane, and the airport A1 is close to or nearby location L1. The airport A2 is nearby location L2, and there exists a flight connection with this plane from airport 1 to airport 2. And this gives us the possibility to instantiate such a transportation means by a plane and replace this abstract state feature, this abstract precondition with these more concrete one, and so on and so forth. Well, concerning plans and methods, so a plan is defined as a 4-tuple, so we have a set of plan steps that represent tasks. We have a partial order on this task set, on the task in this set. We have variable constraints that reflect instantiations of variables, but also may contain equalities or inequalities between variables or variables and constants. And we have this feature of causal links. And a causal link presented this way is just representing that we have a task T1 and a task T2, and the task T1 has as a precondition a condition or formula phi, which is a precondition of this second task. So this means task T1 establishes the precondition phi for this task T2. Well, and the methods define decomposition options of abstract tasks, and they consist of the abstract tasks for which they represent a decomposition together with a plan. And this plan may contain abstract or concrete tasks, like in the definition here, in order where variable constraints and causal links. So such a method says just it can replace an abstract task by a plan. So in the formal background I introduced, and then this first order predicate logic we have as a background allows for formal notions and even the proof of formal properties of plans and methods. And one example for this is the legality of decomposition methods. And this says if we have a method M to decompose an abstract task T by this plan, then this method defines a legal decomposition, or we say also an implementation, a correct implementation of these abstract tasks, if and only if each sequence of tasks that can be built from T complying with the partial order, complying with the causal links, and complying with the variable constraints we have, then each such sequence, so each linearization of the plan in this method, each such sequence transforms a state in which the precondition of these task sequence holds into a state S prime where the postcondition of this task sequence holds. So the precondition of a task sequence can be viewed as a condition that enables that the task sequence is actually executable. So that each task can be executed in the order given by the sequence, and we finally end up with a postcondition of this plan that is a formula that is in some sense produced by this task sequence. And it has to hold, and this is the essential point concerning this legality, namely that the precondition of each of these task sequences implies the precondition of the abstract task, and the postcondition of this sequence implies the postcondition of the abstract task. And that means then we have an implementation that is sufficient to achieve the postcondition of the abstract task. Well, now what about planning problems? Planning problems are defined by this tuple, namely consisting of the language, so the language with all these symbols we need, the predicate symbols and the task symbols and so on, a set of tasks and a set of methods for the abstract tasks in T, which basically means that is a kind of domain description or domain specification, planning domain specification, is the first three elements. Then we have a description of the initial state, we have a goal condition, and we have an initial partial plan. And a partial plan is a plan that is not yet a solution, and a partial plan may be just one abstract task. Well, and a partial plan with a set of tasks and a partial ordering, variable constraints, and a causal link, and a set of causal links is a solution of this planning problem if and only if P is a refinement of P init, and I will explain this shortly what refinement means in this context, is a refinement of the initial partial plan. The ordering constraints and the variable constraints are consistent, and each precondition of a task in this set of tasks is supported by a causal link from a task that is also in these tasks in the task set of the plan. And the partial order accords with the causal links, of course. So if I have a causal link of this kind, then of course this task Ti has to be executed before Tj. And no causal link is threatened. That means the partial ordering is guaranteeing that it is not possible to insert a task in between Ti and Tj. Once we have this causal link, it is not possible to place a task in between these two that has a non-phi as a post-condition. So that means it is actually guaranteed that this causal connection holds, and it is always possible that Ti produces the precondition of Tj. So no causal link is threatened. And I have nothing said about the tasks. So actually, the tasks in this task set may all be primitive, so that is the usual way it is defined in HDN planning. But in our case, in hyperplanning, it is not always required that the tasks are all primitive. So a plan can be a solution even if the plan contains abstract tasks, provided that the solution criteria holds. But the abstract tasks then can be used. For example, they can be refined or concretized by the human user or by any system or whatever. So we just leave open for some tasks how they actually are performed. That is not prescribed by the plan. We just leave it open. But in the standard case, it is required that all tasks are primitive. So what are refinements? Refinements are, as in HDN planning, task decomposition. It is also the decomposition of state features. So we can just apply a decomposition axiom to an abstract state feature and refine the plan this way. So deciding, for example, which transportation mean to use beforehand, before doing any further refinements. Task insertion is such a refinement step that is adopted from partial order causal link planning. Causal link insertion, so establishing preconditions of tasks, is such a refinement operation. And also the insertion of ordering constraints and variable constraints and bindings. Well, before coming to an example, I will give you a short introduction in what Stefan was already mentioning, namely this companion technology, and I was asked to talk more about planning than about companion technology, and therefore I give just a very brief introduction. So this endeavor is aiming at developing a companion technology for cognitive technical systems, and companion technology means to enable technical systems to be companionable, to be very smart in a sense, and this is actually defined by certain properties of the technical system. So we would like the technical system to provide an individual functionality, so a functionality that is individually tailored to the specific user that is using the system. It consists of the property that the system is adaptable, so it can adapt to changes in the environment. It can adapt to even the changes in the emotional state of the user or his disposition. it is trustworthy, and it has all these nice properties that make a technical system companionable. And in this research endeavor, we try to achieve these companion characteristics of technical systems by providing cognitive capabilities to the technical systems, and achieving these characteristics like individuality and adaptability and so on, achieve these through the interplay of all these cognitive capabilities we have given to the system. And from the AI point of view, it just means, but it means to actually close the perceive, reason, action loop. So here we have perception, so we can recognize what the user is doing. We can recognize by analyzing various parameters of the user, like mimics or gestic or whatever, in order to get an estimation of his emotional state and changes in his emotional state. So here we have perception, then we have a huge knowledge base, we have planning and reasoning to provide this reasoning, and then adapt the functionality of the system and also the interaction in order to come up with an individualized functionality and presentation of functionality to the user, on the one hand, which respects the individual needs the user has, respects his background, his knowledge, his mood, and so on. Well, and planning, of course, is at the heart of such a system. And the role of planning actually is that the adaptive functionality of the system is provided through planning, either by having a plan that controls the system, the technical system, or by having something like an assistant, a digital assistant, that gives help to the user in certain situations and for certain tasks. Well, and the role of the planning system is that it has to generate plans of action, of course. It has to present a sequence of actions, and that is not trivial because normally we end up with nonlinear plans, and the challenge here is to find an appropriate linearization of the plan, so an appropriate sequence, a sequence that appears plausible to the user, and we have to present then this sequence of steps. We should be able to explain these on demand. We have also to recognize when this demand is there. We have to monitor the plan execution somehow, and in the case of planning, we do this by plan recognition technology we have developed for hybrid planning. And we should be able to identify execution failures from plan recognition, so we have to differ between deviations the user does that are not relevant and deviations that really corrupt the plan, and then we have to provide alternative plans, or even should be able to repair the failed plan so that the user can set up and can achieve the goal anyway. So in this planning system is integrated in a prototypical architecture for such a companion system. So where we have here sensors and the sensory analysis providing the world state to the knowledge base. And here also we have a huge amount of background knowledge and planning knowledge and the planning domain model and so on. And then we do planning and plan execution, and we have a dialogue management and interaction management, and finally a user interface in order to present what we suggest here and have generated here adequately to the human user. So next I will present you an example for such an assistant system, and this assistant system is a digital assistant that helps you in setting up a home entertainment system, where you have various devices. You have a Blu-ray player, you have a satellite receiver, you have a television, and so on, AV receiver, and you have various cables, and then you are standing in front of all these devices and you have to construct your home entertainment system, and the assistant is helping you in doing so. So that means, first of all, we have to plan. And here we see how we actually construct such a plan of action in this hybrid planning framework. So we have, on the one hand, the initial state with all what we know about the initial state. We have here the goal state, and what we see here is just a sub-problem of this whole entertainment assistance. It is just a sub-problem where we have already achieved a partial plan. We have here two goals, namely that the AV receiver has to get the audio signal in order to provide it for the speakers, and the TV has to get the video signal. And we have two set-up actions, namely one saying that we need to provide or to set up the AV receiver in a such that the audio signal can be achieved, so that we can close here this connection, and also we have to provide somehow the video information to the TV. So that means here we have still abstract tasks, because we still do not have decided how to actually do these set-up actions. We have here causal links, namely that here this post-condition of this abstract task provides here this precondition of the goal task. So we have these artificial goal task, which has as preconditions the goals. Like in the initial state, we have artificial initial task that provides all the preconditions for the whole thing. So then we have various methods available to provide the AV receiver with an audio signal. So we can use the satellite receiver for that, or we can use the Blu-ray player. In this case, we will use the Blu-ray player, and we'll establish that we can use the Blu-ray player. So then we decompose this action and replace these abstract actions by these two primitive tasks, namely these two plug-in actions or tasks that simply say that we connect the Blu-ray player with a cinch cable to provide the audio signal, and we plug in the cinch cable to get the audio signal from the Blu-ray player to the AV receiver. So we have to plug in the cinch cable, or the opposite side of this cinch cable, to the AV receiver, and then we have closed this chain and can provide the audio signal of the Blu-ray player finally to the speakers. So, and we proceed with this refinement. We can even insert further actions if needed, for example, and then finally can complete the plan structure and can end up with the plan. So then we have the plan completed. We have provided a solution, and now it comes to present the solution to the user. And this means we have, as a planning system, to prepare for this user companion system interaction. And that means the plan steps have to be transformed into natural language sentences, like we see here. So one part of the plan, for example, is translated into a sentence saying, well, connect the SCART output port TV or the satellite receiver. In the case we have, in the part of the plan where we have provided the use of the satellite receiver with the SCART end of the SCART to cinch cable, and so on. So having this text ready, it comes to creating the dialogue with the user. So we have to make use of a dialogue management system, and finally of an interaction management, and then the user interface in order to come up with such a
SCART to cinch cable shall be connected with the satellite receiver as depicted.
Done?
The video end of the SCART to cinch cable shall be connected with the AV receiver as depicted.
Done?
The audio end of the SCART to cinch cable shall be connected with the AV receiver.
Okay.
Well, so far everything goes well. In some cases, it may be a good idea to explain what the system recommends and suggests to the user. In particular, the user asks questions, for example. And here we have the big advantage in this high-planning formalism that we produce what we call knowledge-rich plans. And this means that we have, on the one hand, structural information on plans. So we have explicit causal and temporal dependencies as part of the plan, and we have explicit variable instantiations, and we can use this information to provide explanations. And we also keep information on the plan genesis, so in particular which task decompositions and which task insertions have been done in order to generate the plan. And this enables us to visualize the plans in a focused and adequate manner, and also give explanations of plans. And these explanations are generated by formal descriptions of plan components and the relationships between them. That means we generate formulas representing properties of the plan steps we have. So, for example, we can state that a certain plan step is necessary, or that there exists a causal relation between two plan steps, and we can say something about what this condition, this causal relation actually is, namely here this condition C, and also we can express the decomposition relation between plan steps. And this means we establish possible explanations as axioms of a proof system, of an axiomatic system. And so we have formulas or axioms like saying, well, once plan step S2 is necessary and there exists a causal relationship between S1 and S2, then also we can derive that S1 is also necessary. And the same for decomposition relation. So if there is a relation, a decomposition relation between S1 and S0, and between S2 and S1, then there also is one between S2 and S0. So we can reflect the abstraction hierarchy we used during plan construction this way, reflect them within logical axioms, and can use them in proofs in order to produce a proof chain, and from this proof chain, by backward reasoning, backward chaining, we can obtain then a chain of arguments, and can transform this into explanations. And as we will see here, how these explanations are presented.
Cable shall be connected with the Blu-ray player as depicted.
Didn't I already connect it? Why should I do this?
You have to connect the Blu-ray player with the cinch video cable to be able to connect that cable with the AV receiver. So the audio signal is transmitted from the Blu-ray player to the AV receiver.
Oh, okay.
Well, but with these hyperplanning formalism we do not only do these applications, but we also do research on theoretical properties of this formalism. And there are two main directions of research. One is towards the expressivity of hyperplanning, and this is just done by a systematic investigation of various sublanguages of hyperplanning. So hyperplanning is a very complex formalism, and not for all applications we have, we need really the full expressivity of hyperplanning, but in some cases we also can use less expressive languages which can be handled better and are tractable in some sense. And we do this investigation by establishing an analogy to formal languages and using the Chomsky hierarchy as a reference framework. And most of this work has been done by Daniel Höller and colleagues. And it consists in having a translation or transformation of a planning problem into a formal grammar, and then set up a relation between the set of words that can be derived using this grammar and the set of solutions that can be obtained for this planning problem at hand. And these investigations finally result in such a hierarchy and such a classification of planning formalisms and their relation to formal languages. And if you would like to hear more about this trend of research, then you are invited to attend the talk of Daniel tomorrow in the afternoon, where he will explain more about these things. And the second direction of theoretically oriented research is concerning the important question of efficiency of hyperplanning. And we have obtained complexity results for various problem classes here, and we succeeded in setting up a number of informative heuristics. Most of them are relying on this task decomposition graph. This is a bipartite graph where we relate tasks and methods in such a way so that we have, for example, here task T0 and two methods to decompose these tasks. And the method contains a plan which contains a set of tasks, here T1 to T3. And here we can see that some of the tasks are inevitably to be executed in order to come up with a solution or in order to have a solution. And this is what we call landmarks in hyperplanning. So some of these abstract or primitive tasks actually are landmarks and have to be passed by any plan that is a solution to the problem. And this is one means we use to come up with heuristics by estimating, using this task decomposition graph, the destination of a certain partial plan to a final solution. And we also adopted and modified delete relaxation, or we developed and adopted a delete relaxation heuristics for partial order causal link planning, and also transmitted state-based planning heuristics to this framework and are able to apply them into this framework. And Pascal Bercher has done a lot of work in this context. So the system we have developed and we are using is the PANDA system. PANDA stands for Planning and Acting in a Network Decomposition Architecture. And this hybrid planning framework provides a variety of functionalities, including plan repair, plan explanation, plan generation, of course, where we do this by heuristic search in plan space. And we have recently also done an approach on implemented we started in the early 2000s, and that means we now have a third generation of this planning system, and in this third generation we included also facilities for mixed initiative planning, and there is also a theoretical contribution by Gregor Behnke about how hard it is to change a plan, because changing a plan is essential in mixed initiative planning, because the user may ask to the planning system to exchange a task by another one, and then this has to be computed and has to be explained whether this is possible or not and which consequences this has. And if you are interested in hearing more about this, Gregor will give the talk also tomorrow in the afternoon. And that brings me to many thanks for all my collaborators, and also many thanks to you for your attention, and I'm happy to take your questions.
Anybody who's going first? Yeah. You can speak up or.
Susanne, you're interactive application with Dialog. I don't know if you have addressed the one problem that, in my opinion, is interesting. The differences between the users that you interact with. Because in my opinion, the interconnection between the user planning and the personalization of plan is something that should be taken into account. I don't know if you have touched upon in your project, or you are considering touching upon it.
Yes, you're right. This is, of course, very important, and we are addressing that because we have in the background a user profile or a user model where we know about the user, whether, for example, he is experienced with these technical devices or not, whether he knows what a cinch cable is or not, and all these kind of things. And this guides the planning process in some sense, but it even more guides the explanations we give, and also the time point where we give the explanations. And here we have to rely, of course, on all these perception facilities indicating us whether the user is confused or looks confused or isn't reacting, and then intervention is necessary, and we can explain this to the user. And another point is about this plan linearization, I was saying. So this also depends from the environment where you are in. So, for example, is it practical to take one device and put all the cables you need into it and then come to the next device, or just following the signal and lining the devices in the way the signal is processing? So these are also these things that are open and that have to be considered.
Yeah, I'm just wondering.
Sorry. This guy was first.
Okay. Thanks, Susanne. One question about the explanations. So I presume that it is often the case that there are several explanations for a particular step, or several ways to answer a user query, or things of that sort. Can you give us an intuition about how difficult this is, and to what, and question sort of an attached question would be, what kinds of explanations can one afford within a reasonable time, let's say, for computation?
Yes, so for the time being, we are only able to answer to questions, why should I do this action? And explain this either by revealing the causal chain or the decomposition hierarchy. And it is, there are two problems. The first problem is that explanations can be very long because they relate to the planning process, which could have taken long to come up with a primitive action. And then we have so that means we have to identify which steps are really relevant for explanation, or which parts of the causal chain are really relevant, and we have to decide whether to argue from a hierarchical point of view or not. And we have not yet investigated in which case which explanation is really the most appropriate one. Because this also, so therefore we have to rely on user studies. We did some with this application, and there it was very useful for users that were not that familiar with technical devices that we came up with these explanations, but they were actually very short and very intuitive.
Okay.
Hi. I'm just curious, so you might find yourself in situations where you're offering automated planning for a user who's actually very experienced in that particular area. Is there a way to try and incorporate a tighter integration so that the user can actually contribute to building the plan as opposed to kind of asking the odd question along the way? I'm just curious about that.
Yes, this is done in this mixed initiative planning, so where you can, which is really a collaboration between a user and the system. And so, and there you can say to the system, well, plan for this task, or make suggestions, or you can even by yourself select which actions to take, which actions to insert into the plan, or which actions to remove, and then the system can compute the consequences and on demand can tell you about the consequences, your suggestions and your planning has to reach the goal.
Okay. Oh, I have to get up.
I'll just, okay. So the proof system that you showed for explanation looks very, very similar to back-chaining rules for discovering landmarks. I was wondering if you could say something more about that.
Yes, it is actually such a backward chaining on implications and rules, and insofar it's very similar.
Okay. Last question, because we have a tight schedule, so we still have a minute.
In the 1980s and 90s, there were a lot of researchers who were interested in collaborative planning, who felt it was important to have intentions taken seriously. And I'm thinking of shared plans and joint intentions and joint responsibility and shell for teamwork. There were a lot, and I wonder how you feel about that. Are intentions needed to avoid situations invariably going wrong, or are you trying to work outside that?
Yeah, so it is always, so what we experienced is always relevant, that you know about the intentions of the user, not only concerning just the goal that has to be achieved, but also what is in the background and what intentions are in the background. And to respect this in a certain manner, in particular when you like to recognize what the user is doing. So whether he is on track with the plan or with the planning process or not. And this can be respected by taking into account the user model and also the history of what the user has done so far.
Okay, thank you. I was just wondering if the PANDA system, so there are not so many HDM left in our community, they are getting more and more involved. Is the PANDA system somehow available for the community to some extent? Can we make it also to threaten those big problems?
Yes, so we are just in the process of making it available and providing it to the community.
Okay, thank you, Susanne.